Hi everyone, today we continue our discussion on the production of materials with our third topic, ethylene and petrochemicals. Now if you remember, our first two topics covered petroleum refining and ethylene production. Here we've got a model of an ethylene molecule. And I'll just draw the structure of ethylene. As you can see, in the model we have a double bond in between two carbon atoms. And we have 4 hydrogen atoms on the outside. And when we draw models like this, in carbon chemistry, we always have carbons in black and hydrogens in white. So let's look at the reactivity of alkenes. Now alkenes are very useful as raw materials to make different petrochemicals for different uses. Now, because this molecule has a double bond, it's relatively more reactive than alkanes. So what's happening is, across this double bond, there's a concentration of negative electrostatic charge, which is susceptible to oxidizers. So this double bond can be broken and new molecules can be formed. So starting with ethylene, which is the first in the series of alkenes, because it only has 2 carbon bonds. We're going to concentrate on ethylene because it's the simplest. But just remember, for all other alkenes, similar reactions will occur. Now ethylene is widely used for the production of different organic compounds. Now I'll just remind you that ethylene and ethene are exactly the same thing, so don't get confused. Now ethylene can undergo many different reactions, such as addition reaction, which will break the double bond, and also polymerization to make polymers. So let's start by looking at addition reactions of alkenes. In an addition reaction, the double bond is broken and new atoms or groups of atoms bond, forming an alkane that is different from the original alkene. So, as I said, the carbon double bond is broken to a single bond and it forms an unsaturated compound, which means that you cannot put any more atoms over these bonds. And it comes from an unsaturated compound to start with because it's got 1 or more double bonds. So here's a list of a few different addition reactions of ethylene and all alkenes, in fact. So we start with ethylene and we react it under different conditions to get different compounds for different uses. So let's start by looking at this reaction here. The reaction conditions are oxygen and water, and you go from ethylene to a compound called ethylene glycol, which is an antifreeze. So what's happening is the double bond's breaking and new atoms are coming in this case, alcohol groups. So we can also react ethylene with water, again breaking that bond, and we get ethanol with just 1 alcohol group. And we can also undergo what's called halogenation by using a halogen, in this case bromine, to get 1,2-dibromoethane. Now this is the IUPAC name for this compound, and I'll just remind you about how we name this. So what we've done is we've broken the bond and we've got 2 bromo groups on the new alkane. So we have the word di, because that means that there are 2 bromo groups, dibromo, 2 bromos, and we have to count the carbons in the skeleton. There's 2 of them, so it's eth, it's a single bond, so it's ane, and these numbers out the front refer to where the bromo groups are on the alkane. So we name the carbons 1 and 2, so this one we write as 1,2-dibromoethane. And so these rules will always be the same for naming organic compounds. So we'll continue looking at these addition reactions. So here we have ethylene again, and we can go to this compound, which is chloroethene. Now that's the IUPAC name for it, chloroethene, but it also has a common name, which is vinyl chloride. And this is similar to why we have the difference between ethene and ethylene. You have the IUPAC name, and you also have the common name, vinyl chloride. Similarly, we can go from ethylene to this compound here, which the common name I'll just start with is styrene. And the IUPAC name, let's start by counting the carbons. So there's 1, 2, plus 6. This is quite a big group here. I'll draw that for you in a moment. 6 plus 2 is 8, so it's oct. So we write oct. Does it have a double bond? Yes, so it's ene. Where is the double bond? Count the carbons. 1, 2, 3 through to 8 in there. So it's going to be 1 octene. So 1 octene is exactly the same thing as styrene. Now I'll come back to that in a moment. What we can do with these compounds is then have a polymerization reaction, okay, to form polymers. So styrene can go to polystyrene, ethylene can go to polyethylene, and chloroethane, or vinyl chloride, can go to polyvinyl chloride, or PVC, which is used widely in the building industry. Mainly for pipes, because they're non-corrosive and they last longer than metal. So just to show you what's happening with these brackets, we're breaking our double bond up, and we're left with 2 extra arms on the carbons to form bonds. And if you put these monomers into a reaction solution, they will link up with more of these units and you'll get polymers. But we'll go into polymers in our next lesson. Now just remember, this little n here just means a number. It could be 100, it could be 1,000. It depends on the uses and how large the polymer we want to make is. So just before I leave this board, I just wanted to show you this group here. This is actually a benzene group, okay? So I'll just start by drawing our ethylene backbone here. Now this group is actually cyclic, which means it's in a circle, and there's 6 of them. So we can draw this. See, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Now we add the hydrogens. There's 5. 1, 2, 3, 4, 5. But in this molecule are more double bonds, because as you can see from the carbons, they're only bonding to 3 other atoms. But we know that carbon has a valence of 4, so therefore there's double bonds in this molecule. So double bond, and double bond. So there's 3 double bonds in this molecule here. So if I just circle that, I'll show you a neat organic chemist's shorthand for this molecule. Instead of drawing this molecule, we would draw it like this, with just lines. And that's just a shorthand version and a quicker way of writing this. And all it means is, on every corner of this molecule is a carbon atom, as you can see here. And this circle means that there are 3 double bonds, and that the electrons are actually moving around in between the carbons. So these double bonds aren't strictly rigidly there. The electrons actually move in between. Excuse me, I should have put that double bond there, and I should have put that one there. I'm sorry about that. We all make mistakes sometimes. So that is a benzene molecule, and it's exactly the same as that. It's just a shorthand. So moving on from addition reactions, just get rid of this. Now just keep in mind that there are hundreds and hundreds, if not thousands, of different addition reactions that you can undergo with alkenes. So let's look at hydrogenation of ethene. What's happening here is we're reacting ethene with hydrogen to make ethane. So we're breaking that double bond, and the hydrogens are coming in and adding to this molecule. So these are examples of more addition reactions. The reaction conditions for this reaction are that we need a metal catalyst, and we use either nickel or platinum. So going back to this one, hydrogenation, so we need a catalyst, otherwise this reaction is too slow. And as I go forward, you'll see that some of these reactions need catalysts, and others we just need different temperatures, pressures, that sort of thing. But you will have to remember the reaction conditions. So now on to halogenation. So what we're doing is we're adding a halogen to ethylene, in this case bromine, and the double bond breaks and the bromine adds on to form 1,2-dibromoethane, which I discussed earlier. And halogenation, you can use different halogens other than just bromine, such as chlorine or fluorine. Okay, so as I said, the halogens are incorporated. Now we'll look at hydration of ethene. This is where ethene and water make ethanol. So here we have the water molecule being incorporated over the double bond to form ethanol with an OH group, or an alcohol group as we call it. A catalyst is needed once again, either dilute sulfuric or phosphoric acid, which is H2SO4 or H3PO4. Now on to oxidation of ethene. This is where we go from ethylene to ethylene glycol. And this is the formula, the structural formula for ethylene glycol, as you remember, with the two alcohol groups. Now there's two different ways of oxidizing ethylene, either with dilute potassium permanganate, which is this formula here, potassium permanganate, which is an oxidizer. And these are the structural formulae, which are good for you to see what's happening in the reaction, but to cut it down into shorthand, we can just write the molecules themselves. C2H4 gas with KMNO4 goes to C2H4 OH in brackets 2. And this is a liquid, ethylene glycol. And another way to make ethylene glycol is with different reaction conditions. In this case, oxygen and water. And you get exactly the same products. Ethylene glycol I'll discuss in a moment, just for you to know that it's an antifreeze. So here we are with ethylene glycol. It's an antifreeze and it's used in car radiators. Now we don't really need ethylene glycol here in Australia because it doesn't get cold enough. But overseas where it does get cold, they need to put ethylene glycol in their cars to prevent the engine heating up. Now ethane diol is simply ethylene glycol. This is just the IUPAC name for it. Okay? As I said, ethylene glycol has a lower freezing point and a higher boiling point than water. So it allows in the radiator for the water to not freeze. Okay? So just looking at our IUPAC name here, I'll just draw it again so you can remember the structure. If you'll remember, it's an alkane with two OH groups. Oops, OH. And so 1,2 ethane diol, these are the functional groups, the OH groups. And when there's two of them on an alkane, it's called a diol. So this is ethane, because it's single bond, diol, and the 1,2, again, name the carbons, is the position of these functional groups. And another great thing about ethylene glycol is that it doesn't cause corrosion, so it won't ruin your engine. Now, ethylene glycol is also used in the manufacture of magnetic tapes and photographic film, although I guess we don't use too much of that anymore in this digital day and age. And it's also used for making synthetic fibres. Now, other products of ethylene, there are hundreds and thousands of them, but here's just a few. Also used to make intermediate compounds, which we saw earlier with our addition reactions, such as styrene to make polystyrene, vinyl chloride to make polyvinyl chloride or PVC. And these end products are polymers with certain characteristics pertaining to their applications. So looking at polyethylene, about 60% of ethene is used to make polyethylene, which is a very important and useful polymer. And I can tell you that I've got plastics all around me, we all do, and I couldn't actually imagine life without plastics because we use so many of them. Packaging, you know, pens for example, all sorts of things, like in this picture here. Now, so it's used in general plastic applications. So now let's look at some products that we've discussed today and their specific uses. So we started by looking at polyethylene. It's used for plastic film, crates and pipes. Ethylene dichloride is used as the raw material to make the vinyl chloride monomer for PVC production. We've looked at PVC, briefly, polyvinyl chloride, for plastic pipes, for gutterings and for soft furnishings. We looked at ethanol. Now ethanol is a solvent, an organic solvent. It's also put into fuel and it's also as a drink, alcohol, alcoholic drinks. We also looked at ethylene glycol, which is used as an antifreeze, polystyrene for plastic packaging and insulation. We looked at 1,2-dibromoethane, which is a petrol additive. It actually increases, dibromoethane as a petrol additive, and chloroethane. These two are also solvents, okay, organic solvents. So chloroethane as a solvent and also as a refrigerant, either in fridges or in cars. So now we'll look at the last type of reaction that I'll discuss for today, which is substitution reactions of alkanes. So we're starting with an alkane, and as you know, alkanes are saturated, so there's no double bond we can break. So you can't add anything, we need to just substitute. So here we have bromination, where we're using bromine, and we're adding a bromine, and one hydrogen comes off to form hydrogen bromide, and here bromoethane. And again, with halogens, we could use chlorine or fluorine for different uses of different molecules. Now this substitution occurs in the presence of UV light. So it doesn't happen by itself. In the lab, we'd have to use a UV light for the reaction to take place. And if you remember, that's because alkanes are not very reactive. So we need to push it along. So that wraps up what we've been talking about today with the uses of ethylene and the different organic reactions that we can use ethylene for to make different products for different purposes, such as plastics. So let's start with our questions now, and question 11. Why are alkenes more reactive than alkanes? Now, this is because alkenes have a reactive double bond. As you can see from this addition reaction, we can break that double bond and add other molecules over that bond to produce here, for example, 1,2-dichloroethane. And as I said earlier in the lesson, the double bond creates a concentration of negative electrostatic charge over that double bond, which means it's very reactive. Now question 12, identify the homologous series and functional group that describes ethylene. And you've been given some choices here. This is the homologous series, alkane, alkene, alkyne, and alkanol. And these are their functional groups. A single bond, a double bond, a triple bond, and an OH group. So where does ethylene fit into these groups? Of course, it has a double bond, so it's an alkene. So that's our answer for this question. Similarly, if it were to ask for an ethylene group, it would be a triple bond. So question 13, what is meant by a substitution reaction, and does an alkane or an alkene undergo these reactions? Well, it's alkanes, because one atom is substituted for another. It's not added, it's substituted. So remembering back to our diagram here, with the bromine comes in and a hydrogen comes off. So just remember that it's alkanes. So as I said, for example, a hydrogen atom can be replaced with a halogen atom, but light energy in the form of UV energy is required. So just to recap, as I said, this could be a chloro group or a fluoro group, and substitution reactions are always with alkanes. And these reactions are slow. As I said before, we need UV light to get them moving along because alkanes are not very reactive. Now question 14, what is meant by an addition reaction, and does an alkane or an alkene undergo an addition reaction? Well, it's an alkene because we need a double bond to be broken, opening up new bonding sites for different atoms or groups of atoms. So your answer to that is an alkene. Now these reactions are normally spontaneous because the double bond is very reactive. Okay, so here we have hydrogen breaking that bond to form ethane in that example. And yes, just to recap, it involves alkenes because they are reactive and they are unsaturated compounds. And remembering this word, unsaturated compounds have a double bond, which can be broken to form alkanes. So finally for today, question 15. Outline 4 applications of industrial ethanol. First of all, ethanol is an industrial solvent. It's used very, very widely for all sorts of reactions and to make all sorts of different products. It's also an additive to fuel, and this is to lower emissions of dangerous gases such as carbon monoxide. And you may see at your fuel pump E10 or E15, and that relates to the percentage of ethanol that they put in the fuel mix. Another application is in pharmaceutical applications. Ethanol is a good antibacterial, so things such as antibacterial soaps, and it's also used in things such as mouthwashes. And finally, it's also used in the cosmetics industry for various different things, as you can see here, a range of ladies' products, and also in perfumes, ethanol is mixed in. So that wraps up our discussion today with regard to petroleum refining. And in our next lesson, we'll be discussing polymerization, which stems from what we were talking about today with regard to PVC. Okay?